Today we take a look at lesson 4, which is solving rational expressions. So we're going to be looking at equations today. And this is part 1 of a 2-part process. Tomorrow we'll do the last lesson, which will be part 2. One thing I want to note here at the beginning is that within the Play Pause It, you will be completing some practice problems that are not on this page. So you may want to pause the video at this point and go get something that you can write on if you didn't print this out. Because I will be posting in the Play Pause It some additional practice questions that you'll be asked to complete. All right, so solving rational expressions. So how do we do this? Just like in all of the previous lessons, the first thing we're going to be looking at doing is factoring. And we're always focused on the denominators for this style of questioning. So first step here is we want to factor all the denominators when possible. Because after we do that, then we're going to do 2 things we did last week. Identify domain restrictions, which is, again, setting that denominator equal to 0, finding all the places where x cannot equal a value because we get a 0 in the denominator. And then step 3 is to find the LCD, and we're going to do that the same way we did last week. Step 4, once we have our LCD, we're going to multiply every single term in the entire equation by the LCD, and that'll help us eliminate the fractions. And then lastly, we'll solve the remaining equation, and we'll find that over the course of today and tomorrow, some weird things can happen, so be prepared for that as well. Especially because now we have these domain restrictions. So if you get one of those, we'll talk about what does that mean and how do we work with it. All right, so let's take a look at example 1. And give yourself lots of space here to write because these are potentially going to take up a lot of space. All right, so first and foremost, we want to factor. Good news for us, x plus 1 and x minus 5 in the denominator already factored. So we don't have to worry about that for this one. Step 2 is going to be to find the domain restrictions. And again, domain restrictions are anywhere that the denominator, either one of them, equals 0. So x cannot equal, if we look at x plus 1, it can't equal -1. If we look at x minus 5, +5 would create a 0, so that won't work either. So we want not equal to -1 and +5. So at the end, in that step 5 that we were talking about at the beginning, if either one of those are solutions, then they're technically not our answers that we want here because they don't work. Now, second step in this case is to find the LCD. And the LCD is every part of the denominator that we didn't highlight in addition to any highlighted pieces. Because our denominators are both different, the LCD is simply going to be those 2 denominators multiplied together. All right. So now the place where we need to show a little bit of work and take up some space, and that's because we're going to multiply this denominator, or LCD rather, by both of the fractions in this case, because there's 2 terms, one on each side. So I'm going to write it, squeeze it in off to the side on each. We're going to do x plus 1 times x minus 5 over here, and an x plus 1 times an x minus 5 over here. Now, the wonderful thing that should happen when you do this is that every time we should find that, let's get rid of these lines, something should cancel out because when you built the LCD, you used each denominator in building it. So over on the left, since the denominator is x plus 1, this x plus 1 will cancel with it. So really what we have to do is just multiply these 2 factors together for this first side. Over on the right, we have the denominator is x minus 5, which means I don't need this x minus 5 because they would both be top and bottom. Okay, just like we've been canceling in rational expressions. So really over here, I just need to multiply x plus 2 times x plus 1. Now in both cases, those are binomials, so we're going to either use a box or the FOIL concept. And in the interest of space on our screen here, I'm going to use FOIL, but you can certainly set up a 2x2 box for each one and multiply. So on the left, we're going to get x times x to be x squared. Then we'll get plus 5x minus 5x, and the last term would be minus 25. Now, because we canceled out the denominator, I don't even need a fraction on that side. On the right-hand side, x plus 2 times x plus 1, again, FOIL or box. So x squared, then we'll have plus 1x plus 2x plus 2. again, because the x minus 5 is canceled, I no longer have a denominator on that side either. So the good news is, in this step of multiplying by the LCD, I completely get rid of the fractions, and now I'm looking at a one-level equation. We can do this. Now, the other great news is that as I continue to start solving, I'm going to combine like terms to clean this up a little bit. So over here we'll have x squared. The 5x's actually cancel out, and I just have minus 25. On this side I have x squared plus 3x, combine those two x's, and plus 2 on the end there. Now when I start to solve, again, we want to keep x squareds and things positive, so I'm going to choose to move everything to the left. But in this case, the x squareds actually cancel out entirely because x squared minus x squared is gone. So this equation becomes negative 25 over here equals 3x plus 2. So I don't even have to deal with the squared sign anymore. I'm just solving for a regular x. So at this point, I don't care what side x is on. I'm going to keep it over on the right now, and I'm going to move over the 2. So we'll have negative 27 equals 3x. Dividing both sides by 3, we get x equals negative 9. Now, very, very important that we do this at the very end here, and that was step 5 from the list above, and that's to verify that our answer is not one of the restricted values that we wrote all the way at the top, which at this point it's getting kind of lost in all of our work. But our restricted values were the x is not equal to negative 1 and positive 5, and if we look, x minus 9 is not one of those values. So I would just simply write, not in highlighter, that our solution here is x equals negative 9. So that is our final answer to the first one. All right, moving along over to example 2. So we see the same type of setup. Our denominators in this case are t plus 1 and t minus 15. They are already factored, so step 1 from above is done for us. So step 2 is to identify excluded domain values. So x cannot equal, in this case, if we look at the first one, a negative 1. And if we look over here, t minus 15, we can't have a positive 15 as an answer. And I'm going to go ahead and highlight this so, again, it doesn't get lost at the end. That's the thing that we need to be checking at the very end when we find the actual solutions to the equation. All right, let's get rid of those. Next step is to find our LCD. Again, looking at this one, just like example 1, there are no common factors between the denominators, so the LCD is simply both denominators multiplied together. And I just noticed that I'm writing x's instead of t's, so let me change those. All right, so t plus 1 would be in our LCD, and t minus 15. All right, next step is to multiply both terms, in this case, since there's 2, by our LCD. So over on the left-hand side, we're going to multiply by t plus 1, t minus 15. Over on the right, we're going to multiply again by t plus 1, t minus 15. And now we look for things to cancel and figure out what we actually have to multiply. So on the left, the t plus 1s are in the top and the bottom. They cancel out. On the right-hand side of the equation, the t minus 15s are in the top and the bottom, so they cancel out. Even better news is, in this case, I don't have binomials here or here. So in that case, I'm just needing to distribute into each of these binomials that are left over. So for the left-hand side of the equation, 3 times t minus 15 gets me 3t minus 45. And that would be equal to, now we've got negative t times t would be negative t squared. And then we have negative t times 1 would be negative t. Now in this case, since there is only one t squared term, it's not going to cancel out. So we are going to have to deal with a quadratic in this case. And just like I was saying on the last example, I want to make that t squared term positive. So if I have to factor, which I probably will, everything, or the coefficient is positive in this case. So first thing I'm going to do is add over the t squared to the left. So that gets me positive t squared plus 3t minus 45 still equals negative t. And if you recall from lesson 3, when we're solving quadratics or t squared terms in this case, we need to be able to factor it. And in order to do that, we have to have the equation equal to 0. So I do have to do one more thing before I factor, and that's going to be to add over this remaining term here. Because now I'll have t squared plus 4t minus 45 equals 0. And now I can do my factoring technique and find the factors and set each of those equal to 0. So let's do our factoring in a different color here. So if we build the x, because we've got a trinomial, we'll have negative 45 in the top and positive 4 in the bottom. Two numbers that multiply to negative 45 but add to positive 4 would be negative 5 and positive 9. So now we go to grouping. T squared minus 5t plus 9t minus 45. First two terms have a t in common, so we'll take that out. Second two terms have a factor of 9 in common, so we'll take that out. And as usual, we get that common factor t minus 5. So I'm going to rewrite this over here back with our rational equation work. T minus 5 times t plus 9. Still equal to 0. And now, just like lesson 3, we're going to set each of those equal to 0 and solve. So t minus 5 equals 0, and t plus 9 equals 0. I'm going to put them together in 1 here. We'll get positive 5 on the left. We'll get negative 9 on the right. Last thing I have to do, again, go back up to our excluded values, negative 1 and positive 15. In this case, neither of those are identical to 5 and negative 9, so I'm going to box this in because we actually have two solutions this time. 5 or negative 9 would make that original equation true.